Most A-level maths students scored no more than 1 mark out of the 5 points available for part A here. This question sets apart those students destined from A stars, from A's, from B's, and from the rest. Let's work through it together so that if one like this comes up this summer, you can feel really confident. It says figure 8 shows a sketch of the curve C with this equation, y equals x to the power of x, where x can only be a positive number. Part A, find, by firstly taking logarithms, the x-coordinate of the turning point of the curve. It says solutions based entirely on graphical or numerical methods are not acceptable. So we've got to show the algebra here for 5 marks. So we'll start with the equation that we were given. Then we'll follow the instruction that we were given. It said find by firstly taking logarithms. So I'm going to take logarithms of base e, i.e. natural logarithms of both sides. So natural log of y will be natural log of what we have here. There's a rule of logs that you should know that says that you can bring this power down to the front. So it now appears here. If you get that far, you get your first mark. Next, because it's talking about a turning point, we need to differentiate this to find dy by dx. To do that, I'm going to differentiate implicitly. How do I do that? Well, I just differentiate this natural log of y normally. How do I do that? Well, when we differentiate a natural log, we write it as a fraction. On the bottom of the fraction, we simply copy and paste the argument of the natural log. And on the top, we simply differentiate that. If you differentiate y with respect to y, you get 1. Now, because I'm differentiating both sides with respect to x, I need to slap on a dy by dx after that. Now, to differentiate the right-hand side, because I've got a product here, I've got the product of x multiplied by the natural log of x, I've got to use the product rule. What does the product rule say about differentiating this? Well, it says leave the first item, so it says leave the x as it is, but multiply that by the differential of the second item. If you differentiate natural log of x with respect to x, again, you get a fraction. You copy and paste the argument, which in this case is the x here, to the bottom of the fraction. You differentiate x, that goes on the top. If you differentiate x, you get 1. So, what have we done so far? We left the first item as it is, and we differentiated the second item. Now we're going to do that the other way around. We're going to differentiate the first item, differentiate x, that gives us 1, and we simply leave the second item as it is. If you do all of that, you get your second mark. We can tidy up the right-hand side a little bit. This part, x times 1 over x, well, the x's will cancel, leaving us with the 1 that we have here. And 1 times natural log of x, well, that's just natural log of x. If you get to that nice tidy form, that's another mark. So, we need to find the x-coordinate of the turning point of the curve C. At the turning point, you should know that the gradient, that's dy by dx, equals 0. So, we're going to replace the dy by dx in this formula with 0. If you multiply 1 over y by 0, well, you get 0. Subtract 1 from both sides, we get this. Now we just need to isolate the x. Remember that natural log means log to the base e. So if I want to get rid of this natural log, to get rid of this log to the base e, I can say that x here is the base of the log, e, to the power of the right-hand side, to the power of minus 1. So there we are, x is e to the power of minus 1, or 1 over e, however you want to write it. If you get that far, you get your final 5th mark. Next it says the point P with x-coordinate alpha and y-coordinate 2 lies somewhere on this curve with this equation, y equals x to the power of x. We're asked to show that the value of alpha, the x-coordinate of P, lies between 1.5 and 1.6 for 2 marks. So to help me to write this neatly, rather than writing y equals x to the power of x, I'm going to write f of x equals x to the power of x. Why would I do that? Well, to show that alpha lies between these two values, what I'm going to do is that I'm going to substitute each of these values, 1.5 and 1.6, into this equation that we have here, replacing the x here by 1.5. If I do that, I get 1.5 to the power of 1.5. Putting that in the calculator, I get this value, which is less than 2, less than the y value of p. If I do the same with 1.6, substitute that into this equation for each of these x's, I get this. And if I use the calculator to evaluate that, I get this number, which is greater than 2. If you do both of those things, we get our first method mark. Now we need to write a conclusion. Because this value was less than 2, and this value was greater than 2, and this function x to the power of x is continuous, that means we can draw it without taking our pen off the paper, then it does mean that the value of alpha is between 1.5 and 1.6. If you write that clear conclusion, making sure you refer to the continuity, as well as this being less than 2 and this being greater than 2, with this final conclusion, you get the final mark. Next, it says a possible iteration formula that could be used in an attempt to find alpha is this formula here. It says using this formula with x1 is 1.5, find the value of x4 to 3 decimal places for 2 marks. Let's just copy down the formula that we were given here. How can I find x2? If I replace every n in the formula with n equals 1, then I'll end up with this. And you can see, therefore, that this part gives me x2. So it's saying to find x2, I do 2 times x1 to the power of 1 minus x1. So I'm doing, in this case, 2 times 1.5 to the power of 1 minus 1.5. Let me show you how you can type this into your calculator really efficiently. First, you type 1.5 equals into your calculator. Then we set up the right-hand side. It was 2 times the answer, 1.5, to the power of 1 minus 1.5, the answer. Notice how I'm using the answer key there. If I press equals once, that gives me x2. If I press equals again, that gives me x3. And if I press equals again, that gives me x4. So you can just write each of these values down. Don't forget, at the very end though, we need to round correct to 3 decimal places. So you only need to show the working out for one of these to score the method mark. Otherwise, you can just write down each of the answers. Just make sure you round appropriately, as it says in the question at the end. Part D. Describe the long-term behaviour of xn for 2 marks. Well, again, we can use our calculator here, and if you set it up the way I've shown you, using the answer key, you can spam the equals button many times, and then you'll see what happens in the long term. You see, eventually, this sequence oscillates between 1 and 2. So we say that this is a periodic sequence of period 2. That just means it's repeating, and the repeating units is in 2s. It goes 1, then 2, and then 1, then 2. And it's oscillating between those specific values, 1 and 2. In their report after the exams, the examiner said that in general, this question was discriminated well between candidates of all abilities. They said that Part A was demanding, with most candidates scoring no more than 1 mark. They said in Part A, most candidates took logs as advised by the question, but at this point, a significant number of candidates made no further creditable progress at all. So they got 1 mark, and that was it. In Part B, only a few made any reference to the curve being continuous in the interval. That's important here to score the mark, so don't forget to reference the continuity. Do you think you would score full marks in a question like that this summer? Let me know in the comments, and let me know if there are any other questions or topics you'd like me to review before the exams this summer.